solve problems on the membrane analogy that we studied in the last lecture. So the first example is like this. So we have a shaft with an elliptical cross section with minor axis as B and the major axis being A. The problem is that we need to find out the maximum shear stress in the shaft due to the applied torque MT, and we are going to use membrane analogy to solve this problem. Now we know from our previous analysis that for an elliptical cross section the torque is related to the angular rate of twist in this given form. So for an elliptical cross section, we know that this is the relation between torque and the angle of rate of twist theta for an elliptical shaft. Now let us write down the expression of the shear stress. Okay, so these are the expressions for the two shear stresses in terms of g theta. Now what we can do is that we can plug in this relation here and we can express tau xz as minus 2mt So what I have done is that I have done nothing. I have, in this expression for stresses, I have replaced g theta in terms of mt. Okay, so and therefore we get this shear stresses in terms of mt. Okay? Now these are the shear stress distribution all over the elliptical cross section of the shaft. Now let us use membrane analogy and let us try to find out where the maximum shear stress is going to happen. Now before we get into that, you probably will appreciate that from this shear stress distribution, it is very difficult to find out the position of the maximum shear stress or the value of the maximum shear stress if we don't use the concepts of membrane analogy. So from membrane analogy, so what can we say from membrane analogy? We can say Okay, so we can say that the maximum shear stress is going to happen at the point where there is a maximum slope for the analogous membrane. Now you can visualize the deformed shape of the analogous membrane for this elliptical cross section, and we can probably understand that maximum maximum slope is going to happen at this boundary, which I name as B. Okay, as well as this boundary. Okay, so at the end of the minor axis, we are going to have the maximum shear stress. So if we know the location of maximum shear stress, then it is very easy to find out the expression of maximum shear stress. Therefore, tau max is going to happen at B. Okay, so at B, tau yz is equal to 0. So the only shear stress that I have at B1 and B2 are tau xz. So that is going to be tau xz at B1 and B2. And that value has to be equal to minus 2mt by pi a b square plus 1. Okay, and therefore that is the expression for maximum shear stress. So this is the expression for maximum shear stress in an elliptical cross section because of an applied torque mt. Okay, just to reiterate, this analysis of finding out the maximum shear stress otherwise would have been extremely difficult if we have not used the concept of maximum membrane analogy. Next, I will move into another problem where also we will try to find out the maximum shear stress. Okay, So we have done this problem in the last tutorial, where we have seen why this stress function is a valid stress function for the triangular cross section shown in the figure. Okay, now the next problem that we are going to do using the concept of membrane analogy is that, knowing that this is the stress function, we will try to find out the maximum value of the shear stress in this cross section in terms of theta. So if this is the stress function, let us find out the expression for the shear stresses. Now that we have got the expression for the shear stresses, let us use membrane analogy to see the point where the maximum shear stresses can happen. Now if I imagine the analogous membrane, we can probably understand that the maximum shear deformation, or the maximum slope of the deformation of the membrane is going to happen at the midpoint of the three sides of the triangle. Right? If we just try to imagine the deformed analogous membrane, we can probably appreciate that the maximum slope of deformation is going to happen at the midpoint of the three sides of the triangle. So it is going to happen here, it is going to happen somewhere here, and somewhere here. So at this 1, 2 and 3, we are going to get the maximum shear stress. So 1, 2, 3 is going to have the maximum slope in membrane, and therefore maximum shear stress tau. So now that we have known the position of the shear stress, maximum shear stress, it is very easy to find out the value of the maximum shear stress. So let us do that. Maximum shear stress is going to be tau max, and that is going to be happening at the point 1, 2 and 3. So let's try to find out the maximum shear stress at 1, which is a easier coordinate, and we will be able to find it out. So let us find it out at 1. So at 1, the coordinates are minus a by 3 and 0. Now we can understand that at 1, the value of tau xz is going to be 0, because y is equal to 0. So only shear stress that is there is tau yz. So we are left to find out tau yz at minus a by 3 and 0. If we find that out, we are going to get this as g theta. X is minus a by 3 and minus 3 by 2a squared by 9. So if you simplify this, we are going to get this as minus g theta a by 2, and that is the maximum value of the shear stress. You will see that we are going to get the same value for all other 2 points. So we are going to get the same value of the shear stress at point 2 and at point 3. So now let me tell you this here, that if we had not used the membrane analogy to find out the maximum shear stress, it would have been rather impossible to find out the maximum shear stress for this cross section. So this shows how handy membrane analogy can be in analyzing the structure. So with this, we will move into the third problem of the tutorial. have this problem of a thin wall C cross section. I call it thin wall because the thickness, the uniform thickness T is much lesser than the other two dimensions A and B. Okay, and as I said in the last class, thus B by T or A by T should at least be greater than 10 in order to call this as a thin wall structure or a narrow rectangular strip. Now, let us see how to relate the applied torque T with the angle of twist theta, or in other words, how to find out the torsional rigidity of this cross section. So I can say that the applied torque T can be thought of to be resisted by three components, which is T1 plus T2 plus T3. So T1 is the torque resisted by portion 1, T2 is the torque resisted by the portion 2, and T3 is the torque resisted by the portion 3. Now, if I write down the expression of this torque T1, T2 and T3 from the membrane analogy based solution that we have studied in the last lecture, I can say that T1 is going to be 1/3 g theta A T cube by 3. T2 is going to be 1/3 g theta B T cube by 3, and T3 is same as T1, and that is going to be 1/3 g theta A T cube by 3. So if I sum this up, this is going to look something like this. Sorry, I have written an extra 3 everywhere. So if I sum this up, it is going to be 1/3 g theta 2a plus b into t cube. So that is the relation between torque and the rate of twist theta. And therefore, the torsional rigidity can be written as okay, so this is the torsional rigidity. Now, the second part of the question asks for the maximum shear stress. Okay, the maximum shear stress is always going to happen at the boundary of the cross section. So, the maximum shear stress is therefore going to happen somewhere here, somewhere here, somewhere here, here, here and here. Okay, and the value of maximum shear stress is going to be exactly the same that we had found out in the earlier lecture, and we can write that maximum shear stress okay. So therefore, these are the two fine. So now we understand that if we have any open cross section consisting of thin rectangular cross section, we can very easily find out the torsional rigidity of that section. Okay, now let us move into the fourth and last problem of this tutorial. Okay, so the problem is like this. We have a narrow isosceles triangle, though I haven't drawn it very well as an isosceles triangle, but for a narrow isosceles triangle, we have to use the membrane analogy to find out the torsional rigidity. Okay, the height of the triangle B is much greater than the size than the length of the base of the triangle, which is C0. So B is much more greater than C0. We have to use the membrane analogy and try to find out the torsional rigidity of this cross section. Now, how are we going to solve this? Now, again, try to visualize the deformation of the analogous membrane for this narrow triangular cross section. Try to make the assumptions that we had made for a rectangular cross section, a similar narrow rectangular cross section, and let us see if we can get a good approximation of the deformation and thereby a good approximation of the stress function. Okay, so now if we can properly imagine the deformed shape of the analogous membrane, you can see that the deformed shape is parabolic, that it's always parabolic at any value of y, but it is going to vary with y. The parabola, the width of the what should I say, the length of the parabola is going to change over y. So if I take a cross section in xz plane, it is going to look something like this. So this is going to be C, which is going to be a function of y. So this is at xz plane. So at the base, this is going to be the same parabola, but this length is going to be C0. This is again in xz plane. Okay, so let me just try to reiterate that the deformed shape of the membrane can be very well approximated as parabolic, with the width of the parabola changing with y. So at an arbitrary y, it has a width of c, which is a function of y. Okay, let me write it down. Okay, so from the approximated deformed shape of the membrane, we can see that, say that the stress function is going to be of this form, okay, where C is the width at any y. Now, if it is the stress function, we can relate the applied torque mt in terms of this stress function using the integral. So applied torque mt is going to be So what I have done, I have expressed C, which is the width of the parabolic deformed shape, in terms of the known parameters C0 and B, and in terms of Y. So that we can easily perform the integration. Okay, so MT, which is minus, so which is 2 phi dx dy, can therefore be written in terms of this integral. So let us try to evaluate this integral, okay, and see how is it going to look like. So okay, so if I evaluate this integral, it is minus 2g theta 0 to b, and that is going to be x cubed by 3 minus I hope I'm doing this correctly. No, this is going to be so I will skip the in between steps. I think you can do it better than me. And then the final answer is going to be something like this. If you evaluate the integral correctly, I don't know whether I have done that. So, but it's not a difficult task. So it is going to be something like this. B by 12. So that is the torsional rigidity. Okay, so this is going to be your relation between MT. So your torsional rigidity is Gj, which is going to be G C0 cube by B by 12. So that is the answer. Okay, so therefore we, by using the membrane analogy, we could derive the torsional rigidity of a narrow triangular cross section. So with this we will end today's tutorial session. Thank you.